Porque aquí no me le puse topic, que no está bien.
Sounds like the projector is not
Y yo le dije
working.
que, exacto.
Sounds like the projector is not working, so I'm gonna like explain everything on the board. We started last time talking about lateral load resisting systems, and it was very, very important lecture because you know, like if you are gonna be a building designer, you have to know about lateral load resisting systems. So this lecture also is very important because we are gonna talk about the structural dynamics. But I want to tell you something. If you want to be a building designer, you have to take a bunch of classes. Like you have to be versed in structure analysis basics. You have to be very good at them. That's like structure analysis 1, analysis of beams, frames, and definitely the analysis of slab system because that's the gravity load of the whole building. So once all this, and what I'm talking about right now is a structure analysis. You have to take also, you be very good in concrete design or steel design. You have to be good at design classes so that you can design the gravity system that holding the whole floor system. So you are good at all that. Let's take the lateral system. For the lateral system, you have to be very good in structural dynamics. You have to understand how the structural dynamics is working, and I believe FIU offer 1 or 2 classes in structural dynamics. And if you understand structural dynamics very well, and that's like we're saying it's a complete class. Like you are gonna study something called single degree of freedom system, multi-degree of freedom system, single degree of freedom system, dammed and undammed, multi-degree of freedom system, dammed and undammed. So it's a whole full class of many different types of analysis for the dynamics of structures. By the way, all this is linear. You are gonna do the same analysis with nonlinear analysis and how it's gonna be. So it's a whole big story, and it's one of the most difficult classes in the civil engineering curriculum. Okay, so that's a structural dynamics. So we will be like, oh, I finished structural dynamics and I can design tall buildings or I can design high-rise buildings. No, it's not enough. You have also to study seismic and wind analysis. You have to understand how's the seismic load impact the buildings, how to drive something called responsive spectrum, how to what is the soft story phenomena, what is the damping, how we can make isolated foundations. It's a whole big story. That's for seismic design of building or even seismic analysis. And when you design tall buildings, you have to understand not only seismic, you have to understand seismic and wind. So you need to know how wind is impacting buildings. What is the wind tunnel test for tall buildings? So it's big stories, seismic and wind. I'm not saying that you have to take classes, but what I'm saying is that you can study this by yourself. Like you can download a book, a textbook or something, and you can study all that by yourself. And that's for seismic and wind analysis for buildings. You have also to learn how to design the structural elements. All what we are doing here is just analysis. We are just getting internal forces. How you can use these internal forces to design the structural elements that are exposed to the loads that we got like from our analysis. So you have to know how to design shear walls. Oh my God, shear walls design is a completely different story. I remember I took one class in my master's. It was about the design of shear wall. Just the whole class is about the design of shear wall. Whole semester taking one class because the shear wall has a specific design. We design a ballastic hinge in the first story, and you make the other stories different. And the design of the shear wall manually takes a long time. That's why we use software to do this for us. But you have to understand the basics, what is behind the software. Okay. So what I'm gonna do in this lecture, I'm gonna give 1 or 2 lectures, introduce the structural dynamics and how seismic design is done by the ASCE 716. But this is just a simplified analysis. For detailed analysis, you have to take 1 or 2 classes in these concepts. So what I'm gonna do, I'm gonna just summarize the concept. And this I believe can be very, very good introduction for you when you wanna do more, wanna learn more about this, okay, you're gonna take class on that, okay? All right, so I'm gonna simplify lots of concepts. That doesn't mean they are not like, I'm not saying they are wrong, but I'm saying I'm like simplifying them in a way that make it easier for you to understand, Okay, so if you wanna know the bigger picture, you have to take the whole class. All right, so let me start with like gravity load systems. As a structure engineers, doing structure analysis, what do we want the structure analysis to generate for us? Like, let's say that you have a frame like this, has a bunch of loads, and you are gonna do structure analysis. We discussed this before. Structure analysis is gonna give us what?
Counter forces.
Reactions. What else?
Internal forces.
Internal forces, excellent. What else?
Displacement.
Strain.
Deformations, because internal forces can be transformed into stresses. But the thing is, when we design buildings, we use the internal forces, and then in the design process, it's converting them to stresses and capacity and all this. So the last thing is deformation, right? Like, I want to know what is reaction here, what is the reaction here. I want to know how this structure is gonna performing. So it's gonna be something, for example, like this, right? So I want to know how the deformation look like, so I can know if this deformation, this delta is allowed or no. Is it less than or equal than the delta allowed? That's why I get deformation. Same thing, I get reaction here, so I can design this section to resist this reaction. I get bending moment here, so I design the reinforcement to resist this bending moment. That's why we study structure analysis intensively. Okay, same thing with tall buildings. If you have a building like this, and you want to design this building for lateral loads, we want to know reactions at the columns, and we want to know the normal, the shear, the bending moment, everything at each one of these columns. So I can design the columns, and if you have a shear wall, let's say you have a shear wall like this, you want to know at the base of this wall, not only the base, in the whole, if you want to take many sections, the way we design shear walls, like if you have a tall building, you can make one section each 5 stories. And you take the 5th story and get the normal forces and the shear and the moment and design and replicate this in the 5th story. Because the thing is, bending, shear, and normal and all the internal forces, it changes from a story to another. But if you have 100 story, you cannot design 100 sections. It's gonna be very expensive. You are gonna have the labor changing the formation of the form that they pour the concrete in every story. That's expensive. So that's why maybe you change it every 10 story or something. Okay? All right. So you want to find all the internal forces, and also you want to find if the deformation of this structure, once you apply earthquake weight or wind, delta, like this is, we call it the displacement. And also you want to find if the inter-story drift air was in that level. This is called drift, delta D. From here to here. And this is the total displacement of the building. All right, the drift is the differential displacement between the lower story and the upper story. So the thing is from 0 to this, so this is delta D1, sorry, this is delta D1, delta D2, delta D3, but this one is the delta of the entire building. Okay, so this is the displacement of the entire building. So I want to know all that. I want to get reactions and I want to get delta. But the thing is, when we deal with big structures or tall story or tall buildings, it's very difficult to do analysis. It's hundreds or maybe thousands of elements, and you have slabs, you have columns, you have a lot of things to do with. So we need to simplify this model. When we want to solve this structure manually, like you want to solve it by hand, you need to simplify this structure. So let's see, I'm going to tell you what is the procedures to simplify a 3D structure to be a very, very simple structure. All what we care about is 3 components when we try to simplify this. I want to convert this building into like something. This building is a stiffness and mass, right? So every column has a stiffness, and the thing is, what is the source of mass in this building? The big masses. No, I'm saying in the elements. We have columns, we have beams, we have slab. what is the elements that are the most heavy elements? Slabs. That is 90% of the weight of the structure. Here. This is where you have all the dead load and all the life load and all the rain and the roof life load and the snow load. They are all here at the slab system. Columns, shear walls, all this is around 10% of the weight of the structure. So most of the masses are coming from the slab system. So, and the problem is when you have like an earthquake or something, this mass is the one that makes all the deformation. The thing is you have, like let's say this is my building, all right? So your building is like this and the ground is shaking. The thing is the slab is really heavy and at a really high elevation. So what is gonna happen when the ground shake, the slab keep getting thrown away by the earthquake, right? So the mass is the source of the load on the lateral load system that you have. So the thing is, the more the mass is away from the ground, the more is gonna make this building to bend that way. So the masses at the lower elevation is the one that less contribute to the loads on the lateral load resisting system, and the one at the upper elevation is the one that contributes more to the loading, all right? So that's what happened, and you keep getting thrown that way. And the one that resists the lateral load is the stiffness of the column, right? If this column is really, really stiff, like maybe let's say the stiffness is infinity, this thing is not gonna move. It's gonna stay the way it is. If you wanna shake the ground, I'm gonna go like this. Like the ground is moving and my structure is moving like this. If this is exactly the case that is gonna happen, and this is never gonna happen, but let's say it will happen, this structure is not gonna have any internal forces. If your structure has all the deformation as translation, there is no internal forces is generating in the structural system. Yes?
How can we determine the stiffness of an element? Like, do we use do we solve for K, like the K that we have in dynamics that is like F is equal to K times?
That's actually we are gonna study after the project, but I'm gonna give you an example. When you say stiffness of an element, there is multiple stiffnesses. Are you asking about the axial stiffness? Are you ask about the bending stiffness, the shear stiffness, the torsional stiffness? So every structural element has different types of stiffness. Depends on its geometry, depends on the Young's modulus, depends on the inertia, depends on the cross-sectional area. So all these affect the stiffness of the element. And to calculate the stiffness of the element, I'm gonna give you an idea, and also depends on the boundary condition. Like let's say if your element is hinged fixed and you apply load, this is gonna have different stiffness if you have fixed, because the thing is when you fix here, you are increasing the stiffness. But if you're having this hinge, the stiffness is less. When you have this something like this ruler, you are decreasing the stiffness. So it depends on also the boundary conditions. So it depends on the geometry, on the boundary conditions, on Young's modulus, cross-sectional area, and also the moment of inertia. All this affect the stiffness of the element. And this is like the inertia affect the bending stiffness. Like the more your structure has more inertia, the more the bending stiffness is getting higher. Okay. The more the cross-sectional area, the axial stiffness is getting higher. So it depends on the parameters. But okay, let's getting back to this building. So we are talking about mass and talking about stiffness. There is also one important parameter. It's called damping. Damping is the ability of a structure to dissipate the energy of the earthquake. Sometimes, not sometimes, that happens all the time. When you have an earthquake or a vibration that happened to the structure, some damping happen in the structure, like if you have a joint, let's say it's a steel or concrete, and this joint keep open and close, the friction that happen in the joint dissipate the energy of the earthquake. When you open the joint, sometimes we design joints to be flexible so that the earthquake energy can be dissipated. We call them plastic hinges. Okay, so, and even sometimes you create things in the structure to damp the energy of the earthquake. We call them dampers. Like you make something like this, and you make like a piston or something. When an earthquake happens, the energy getting damped inside this piston. So you put them in places in the structure, so you increase the damping of the structure, so you dissipate the energy of the earthquake. So there is three components that contribute to the performance of the structure during an earthquake: the mass of the structure, the stiffness of the structure, and the damping capability of the structure. So if I were able, and what I need from all this is to find the deformation and to find the axial forces. So if I were able to convert this whole structure to one mass, equivalent mass, and convert the stiffnesses of all these columns to one stiffness K, and convert all the damping in the structures, we usually put the damping like this, like the piston logo, like something like this. And we call it C. If I was able to find the equivalent mass of the structure, and the equivalent stiffness of the structure, and the equivalent damping of the structure, and find this system that is gonna generate, this system is going to generate the same delta that you have here. That is called the equivalent system of the structure. All right, so my mission is to convert this to this so I can deal with only one mass, one stiffness, one C, so I can solve the structure. And this is the simplified model of the 3D model. So let's see how we can do that. I'm gonna give one example. Maybe it's gonna take, I don't know, 15 minutes from us so that you can understand the conversion. But it's really, really important for this and also for the stiffness topic that we are gonna discuss in a couple weeks or so. All right, so let's say I have two systems, and these systems are bars. Do you guys know what our bars is? A bar, it's a truss member, okay? It only takes normal force. I have a bar system like this, a big bar, like very big, and attach it to another one, something like this, and all this is fixed here. And I have another system, a bunch of bars, and all these bars are attached to a wall, something like this, and these bars are attached to a very, very stiff plate here, and I'm applying a load B on both of them. Load B here and load B here. Let's find what is the difference between these systems. Okay, so the equivalent system of a bar, we put a spring, something like this. We make a spring, let's say this is have K1, this is K2, and this is K1, K2, K3. So these bars, we usually represent them with a spring, something like this, and then another spring like this. And this system is going to be something like this. And let me draw. B. And this is B. This is called stiffness in barrel, and this is called stiffness in series. K1, K2, K3. All right, I want to find the final deformation that is going to happen after you apply this here. I want to know how much delta we're going to have here and how much delta I'm going to have here. Let's see the difference between the two systems. The thing is, let me ask you, what is the internal normal force here?
B.
And what is the internal normal force here? B. The internal normal force in every one of these sections is B, right? Because if you cut here and you look from the right, it's B. When you look from the left, it's B. That's the reaction. Same thing here. So the normal force is constant here. But the thing is, this is less stiff than this. So I would imagine that this is gonna have delta 1, and this is gonna have delta 2. Which one is gonna have more delta? The less stiff, right? This is the thing is you have to overcome this first, which is the most stiff one. And it's gonna have delta 1, and the final delta is gonna be delta 1 plus delta 2, right? This system is different. Why? Because the thing is, this system has forced all of them to move together with the same delta. Like you cannot move like, wait, if this is really, really stiff, I'm only allowed to move horizontally. So the thing is, this is gonna move delta, so it's gonna force these three members to move together at the same time, having the same delta. However, everyone is gonna have different forces. This is gonna have force B1, this is gonna have force B2, this is gonna have force B3, all right? So the thing is, this is gonna have the much bigger forces because that's like it's the less stiff member and make a delta. And this one is gonna have the less force because it's a big stiffness and make like the same delta. So let's actually find these forces. What is the value of these forces? Like if you guys remember, do you remember Hooke's law? It's B equal K multiplied by delta. Do you guys have you seen that before? That the B, the force, is proportional with the delta, and the proportionality factor is K, right? That's a very, very famous law. So let's apply this here. So from here, I only have one equation. The delta, the total delta in this system equal to delta 1 plus delta 2, right? So let's find what is delta. Delta is gonna be, like if I wanna find delta from this equation, delta is gonna be B over K, right? So I can see that B over K, K is the equivalent stiffness of the whole system, equal to B1 over K1, because this is related to delta 1, plus B2 over K2. Is that right? In this system, we just know, and I just asked all of you, that B here is equal to B1 equal to B2. The normal force here is the same like the normal force here, equal to B. So all this, I can divide by B. So all this is gonna be gone. So I can say that 1 over K equal to 1 over K1 plus 1 over K2. So if you want to find K, so this is going to be K1, K2 over K1 plus K2. Right? How can I do that? Like you guys can sum these two and you're going to find out that this, or you can keep it like this, 1 over K equal to 1 over K1 plus 1 over K2. If you have 3 barrel stiffness, so 1 over K1 plus 1 over K2 plus 1 over K3. And the series keep going. Are we on the same page? Okay, so this is for this system. So what I did right now, I found the equivalent stiffness of barrel stiffness. What if I have a stiffness in series? Same thing. I'm gonna write it here. Right now, I said that I have a B here. This is gonna generate B1, B2, B3. And the thing is, for this to be stable, B should be equal to B1 plus B2 plus B3. How? You have a B is pulling, like let's say I'm pulling a cord and there's 3 other people pulling from the other side. So everyone is gonna have part of the force from me. Part of it is B1, part of it is B2, but part of it is B3. However, I told you before that all of them having the same delta, delta equal to delta 1 equal to delta 2. So they all have the same delta. So I want to substitute from Hooke's law here in this equation. So this is going to be K multiplied by delta is going to be equal to, I have B3, is equal to K1 multiplied by delta 1 plus K2 multiplied by delta 2 plus K3 multiplied by delta 3. Knowing that delta equal delta 1 plus delta equal delta 1 equal delta 2 equal delta 3, I can divide over delta, so all these are gonna be gone. And this is gonna be equal to K equal K1 plus K2 plus K3. Did you guys get that? So if you have a stiffness, I believe, I'm not sure, did you guys study electricity? The resistance of circuit? So it's kind of the same thing. If you have like resistance in parallel, or batteries in parallel and batteries on series, it's kind of the same concept.
So that
saying that's in parallel, but I think that's in series.
That's in series, that's in parallel.
Yeah.
Yeah.
Yeah, you were saying.
I said the opposite?
Yeah.
I don't know, sorry. So yeah, that's series, that's parallel. Okay, so the summary is if you have the stiffnesses in parallel, you sum the stiffness, direct summation. If you have the stiffnesses in series, you do 1 over k equal 1 over k1, 1 over k2. By the way, this is normal stiffness. Same thing happen if you have shear stiffness. If they all have the same delta, so like all the shear stiffnesses are having the same shear deformation, so that means the stiffnesses are in parallel. If all the stiffnesses having the same force B, so they all are in series, okay? And we're gonna do the same summation to both of them. All right, so let's actually see how this concept can be used in buildings. This. Imagine with me, this is a 3D building. Not 2D, I'm just drawing in 2D. So that's the best I can do now. And let's say this is K11, K12, K13, K4, up to K1N. K1 means the one is story number 1. This is K2, 1. This is K2, 2. And this you're gonna keep going until K2N. And I'm gonna keep going up until KN1, and then KN2, and you keep going until KNM. Like N means the story, M means the column, correct? So you have a lot of stiffnesses. I want to find out a way that I can sum all these stiffnesses together. And I want to see who are in series and who are in parallel. Looking at this structure, when if an earthquake happened, let's say a vibration or a lateral force happened. So what happened is, you're going to have something like this. This is like a vibration or an earthquake acceleration, ground acceleration, happen, AG, the value of the AG is keep changing over time, and this structure is going to keep moving, and let's say this structure make a delta, something like this. Okay, I want you to look at this system. The thing is, when a lateral force happen on a structure, like something like this, the slab is considered, we can consider this slab, we call it, it's a diaphragm. Diaphragm, that means it's a very stiff system in the same floor level. And the thing is, if this slab is moving that way, like let's assume this is the slab system, and there's columns here. This slab system, we call it, it's a rigid diaphragm. Rigid diaphragm means this slab system is very, very rigid. If it moves that way, that means all the column has to move that way with it. If that means if this is a rigid diaphragm. Like if you have a column here, column here, column there, so the thing is, all the columns have to make the same deformation like the slab system. Are we on the same page with that? So if this slab moved, let's say delta 1 here. What does that mean for this column? This column shifted delta 1, this column shifted delta 1. All of them had the same deformation. Same thing here. This story has delta 2, so all the columns has the same delta. This is going to remind you which one of these systems. Stiffnesses in barrel or stiffnesses in series? Sure. Barrel. This one is barrel. So the thing is, all these stiffnesses are having the same delta under the same load. Because the thing is, once the seismic load happens, this is what is going to happen. This system is going to have B1, B2, B3 up to Bn. Why? Because the thing is, the more that you go up, the more that the mass is gonna absorb more forces, or have inertia to take more forces, okay, or potential forces that is gonna happen on this slab. So you are gonna have delta one. So all the slabs under the same force V1 is gonna have the same delta. So that's as a parallel system, like this system. All right. So how about the second story?
By parallel, you mean just because those deltas are all different.
Yeah, I'm talking about only the versus story.
Only the first story.
I'm gonna talk a little bit about the other stories. So for this story, you can sum all these stiffnesses in parallel. And for this story, you can sum all. So what I can do here, I can convert this 3D system to a multi-degree of freedom system, something like this, where I have a mass here, m of story number 1, m of story number 2, m of story number 3, and I keep going up until m of story number n. And I can get the equivalent stiffness of each story, because all the columns and all the shear walls, I can sum of them. And by the way, this is not axial stiffness, this is shear stiffness. Like if you want to make it with a spring, you can make something like this. I can represent it by something like that. This is how the spring look like.
The bottom is deforming a certain amount, the top of the column is deforming another amount. So when we consider the deformation, do we consider only one side of the column?
No,
Or we
this is
consider the
actually
whole
what is the shear stiffness all about. The shear stiffness is about that you have two different deformations.
Okay.
Down is below, so that's not axial stiffness anymore, but it's the same concept applied here. Same thing with the bending stiffness. It's all about the rotation or the differential rotation. So you have this here. So the shear stiffness is the one that is going to control how much deformation you are going to have from below to up. This one is going to be fixed. It's never going to move.
Okay.
But depends on the shear stiffness. This point is going to move a specific amount. All right. All right. So the thing is, I can get the K equivalent of story number 1, K1, and K1 is equal to K plus K plus K. Let's say all the columns has the same amount of K until whatever K n story number 1. All right. So this is going to have K2, K3, K4 until Kn. So every story has different stiffness. That is the first simplification, and this simplification is called multi-degree of freedom system, MDOF, multi-degree of freedom. Can we solve this system? Yes, we can solve this system. But the more that you have, the more stories that you're going to have, the more the system is going to be difficult. I remember I solved maybe 2-3 degree freedom, but more than that, it's going to be horrible. Because the thing is, you're going to have all these, you are going to have matrix. And if the matrix is more than 3 rows, it's going to be, solving the equation is going to be really, really hard. So that's why after 3 it's going to be really hard. But computers can do that? Yeah, computer can do that. Can do the multi-degree freedom system analysis. So what we can do to make this system more simplified? You know, let's look what happened here. This is the deformation that happened in this story. And by the way, this is the total drift. And not the total drift, the inter-story drift. Because this is 0, and this is delta 1. Delta 1 minus 0 is delta 1. What happened in this story, that below has delta 1, and the top has delta 2, but this is the difference, right? And what happened here, like in this story, this is the difference. And this is the difference, and this and so on and so on. This delta is the total delta of each story. Like you have a total delta on the top. This delta on the top is not the inter-story drift. This is the total delta of the building. If you want to find the inter-story drift here, you subtract this from this to get the inter-story drift. But this delta is the summation of the inter-story drift from here and here and here and here and there. Okay? So look at that. How this system from top to bottom is equivalent to each one of these systems. This is the stiffness in series. Because the thing is, you have a stiffness from story 1 is contributing by delta 1, and then this contributing by delta 2. and delta 3 and delta 4, and then at the end, the summation of all these delta is gonna be equal to the total drift, because delta is equal to drift 1 plus drift 2 plus drift 3 until drift n, right? So you can say that the columns at each stories are in series. So you can sum all these stiffness and get one single mass and one single stiffness that can represent this structure, and this stiffness is the series equivalent of all these stiffness. Like K is going to be equal to 1 over K1 plus 1 over K2 plus 1 over K3. The summary is stiffnesses in the same stories are in series, the stiffnesses are in the different stories are in, sorry, this is in parallel, and this is going to be in series. We got that?
Yeah. There's gonna be 1 over K.
This one is the series stiffness. 1 over K1, 1 over K2. Alright? I know it's confusing that you can see
Now he's saying
No,
there's gonna be 1 over K equals,
Yeah.
1 over K1, yeah.
no,
No,
1 over
1 over
K.
K.
equals 1 over K1.
Oh yeah, sorry. This should be 1 over K. Alright, and then once you find the summation, you flip it, and then you get what is the total K. So you have M and you have K. Can you imagine? You have a whole structure, and you can convert it to one mass and one stiffness. So then we can study this structure. Because the thing is, to study this thing and solve an equation for this one is going to be really, really hard. And I'm going to tell you why. Even solving this is really, really hard. Mass and stiffness. And by the way, same thing we can do, and we get the other part, which is the damping. Is going to be, you can sum all the damping in series and all the damping in parallel, and then come with one equivalent damping for the whole system, C. So the thing is, here what happened. A seismic is going to hit the building. It's had to overcome the mass. It's going to throw the mass. And who's going to resist that? The stiffness of the building and the damping potential of the building. The thing is, with the damping potential, like we always say that B is proportional, like B and delta are proportional to each other. So you can say, oh, B equals K multiplied by delta. The B is proportional to the velocity of the structure, and this is for the damping, this is for the stiffness. And you see something, I don't want to say equal to, but the C is always related to the velocity. The damping is always related to the velocity of the structure. But let's not to confuse you. By the way, we usually, when we start the structural dynamics, we start without damping. We say undamped system so that the students doesn't get confused. And once we understand the undamped system, we include the damping in the equation and see what is going to happen. All right? Okay, so let's see why we do all that. The thing is, we do this so I can, my main mission here is to find what is the delta here. That is my main mission. I'm trying to simplify this model, so I can find this delta. So I simplified this model here so that at the end of the day, I want to know how much delta I'm going to have here, because this one is going to be an impossible mission. With this one, yeah, I can do it. So let's see how we can do it. So usually, I'm going to put this system here. K, the damping C, and this is the mass M. Imagine with me, this is the mass of my structure, okay, M. Let's say this mass is going to move on a surface. And this mass is attached to a spring that has a stiffness K. And attached to a damper that has a damping coefficient C, all right? So this system right now doesn't have any external load, but let's say we apply a load F function of T. This is the ground acceleration. If you multiply the ground acceleration, it's going to be F, and usually the seismic load is function of time. So this is a load function of time. So this is my system. Once you apply this load, my mass, this is the neutral axis, like there is no forces. Once you apply the load, this mass want to move this way. MA. By the way, I want you to focus. MA is the final force on the structure. Like AG is the acceleration of the earthquake. Let's say you have, like, I don't want to say Miami because earthquakes doesn't happen here, but let's say Los Angeles. Los Angeles is going to be exposed to an earthquake. When we say an earthquake, what is the AG of the earthquake? What is the ground motion? What is the ground acceleration of this earthquake? It's one ground acceleration for an entire zone. So all the buildings are going to be exposed to the same AG, the same ground acceleration. However, every building is going to have different response. Why? Because some buildings are tall, some buildings are short, some buildings are big, some buildings are small. So everyone is going to show, like if you have a small building, this building is barely going to move, right? If you have a tall building, it's going to have lots of acceleration. So this A is the acceleration of the structure, which is different from a structure to another. Depends on the mass, the stiffness, the damping of the structure. However, Ft is equal to, let's say it is the mass multiplied by Ag, functioned by the Ag of the earthquake. Alright? But let's take it out from here. So Ft is function of the earthquake itself. Maybe all the structure in the same zone are exposed to the same ground acceleration. However, this is not true because the thing is, if you go away from the center, the epicenter of the earthquake, this ground acceleration gets less. So it depends on where you are from the epicenter, this is the ground acceleration. Like if something happened in LA, nothing's gonna happen here, right? Because the whole thing is getting dissipated in the soil. But let's say in the same region, they all are gonna have the same ground acceleration. So I want you to differentiate between two accelerations here because this is really, really important. The acceleration of the earthquake and the acceleration of the structure. And what happened first? The earthquake or the structure? The acceleration of the earthquake or the structure? The earthquake has to happen first, so my structure can have an acceleration. Alright, so my mission right now is to solve this structure with this mass and this stiffness and this damping coefficient to find the acceleration of the structure. Because if you found the acceleration of the structure, you can find the velocity and you can find deformation. Because there's a relationship between A and V and displacement, right? Like if you found the acceleration, you can integrate the acceleration and get velocity. You can integrate the velocity and get deformation. Alright? Okay, so how can we solve this? Let's build the equation of motion here. The thing is, if this mass is moving that way under this force, who's resisting this mass? Is a force, and this is the spring, and the force in this spring is K multiplied by delta, but I'm gonna say this delta is equal to U. Like I'm not gonna say delta, I'm gonna say U, the displacement. The damping or the damping coefficient is gonna generate a force. This force is gonna be C multiplied by V because always the damping coefficient is proportional with the velocity. Okay? So I have two forces, it's gonna resist this, so that mass is it depends how this mass is gonna move. If this force is much bigger than the generated force, I'm sure that this is gonna move with a high acceleration. Like if you have a really, really strong earthquake, so I'm sure that the MA is gonna be that way, right? But if this force is very, very low, so I'm sure that the MA is gonna be very, very low. So if you apply Newton's second law, so the summation of the forces in the x direction, Fx, is equal to MAx. That is Newton's second law. So the force is equal to the mass multiplied by the acceleration. All the forces, all the external forces applied to your body is equal to the mass of the body multiplied by the acceleration of the body. So what is the forces applying on this body? I'm gonna assume that the positive direction is that way, which is the direction of the motion. So I have my forces, Ft is positive, minus K multiplied by U, minus C multiplied by V. By the way, I said that we are gonna use U rather than delta, and I can say that V is equal to U dot and A is equal to U double dot, right? If you differentiate the displacement over time, it's gonna give you the velocity. If you differentiate one more time, it's gonna give you the acceleration. Are we all agreed on that? Differentiate with respect to what? Like if I want to differentiate this to get the velocity, so it's going to be du d what? dt with respect to the time. And you have to differentiate twice with respect to the time to get this. So I'm going to remove v and I'm going to say it is u dot. All this is going to be equal to the mass multiplied by the final acceleration of the structure A, but I'm going to remove A and I'm going to put u double dot. Alright? I'm going to rearrange this equation and it's going to give us a very cool equation. This equation is going to be equal to, I'm going to move these two to the other side and leave ft alone. So I'm going to have, let me put it up there. I'm gonna have m u double dot plus c u dot plus k u equal to the force Ft. This is one of the most important equations in the structural dynamic group. This equation. This is the differential equation of the structure. The structural dynamic differential equation of the structure. If you solve this differential equation, what do I mean by solving? Solving a differential, have you guys solved the differential equations before? It's called partial differential equations, not a normal equation. So, solving this partial differential equation, it's not partial, it's just differential equation. Solving this differential equation, I have to find the value of u. So when I say solve it, I want to find what is the value of u. What is the value of u? This is going to give you the delta of the structure. That's what we need to find. That's why we made all these simplifications. I simplified this structure, and then I come here, and then I know the k, the c, the mass, and then I built all this system to come up with this equation. So let's see what is the component of this differential equation. This component is called the resisting function. This component is called the forcing function. Alright? Sometimes we solve this equation under zero load and we call this free vibration. Like if you put this is equal to 0, so this is called the free vibration equation. But if you put a force here, we call it forced vibration. So if you take a structural dynamic class, we usually do single degree of freedom, forced and unforced, damped and undamped. Okay, same thing, multi-degree of freedom, forced and unforced, damped and undamped. I have actually examples to solve all this. Maybe I share it on Canvas if you got. I have really good notes. Like I summarize the structural dynamics in like 10 pages, but my handwriting is very small. So, but it's really organized. A whole course, like in just 15 pages. If you was able to digest this 10 pages, you are done with the structural dynamics. So if you guys, I can share on Canvas if you guys want to know how to solve this equation. This equation, like, I don't know, like if you guys remember, you assume u and u, like solving differential equation, you say that u is equal, for example, a cosine theta plus b sine theta, and then you say that u dot is equal to the differential of this, u double dot is equal to the double differential, and your whole mission is to find what is the value of b and what is the value of b. So, but this is not our topic. All what I want you to learn right now is that there is a differential equation for this structure and need to be solved, and once you solve this, you are going to find the value of u, the displacement. And that's what structural dynamics do for you. If you want to know how to do it, you need to study structural dynamics. But the thing is, this is really difficult concept. Like, I'm as a designer, I want to design a structure, I don't want to get in all this math. By the way, solving this equation, at least 2 pages of math. So you have to do 2 pages of differential equation analysis and all these stuff. When we do design, we don't want to get involved in all this. I don't want to get involved. And the thing is, this building can be exposed to many earthquakes, can be exposed to large earthquakes, small earthquakes. So I wanna do something simplified or something that is allowed by the code. So let's see what is the codes do to solve the structures. The thing is, as a structural engineers, we don't want to get involved with too much math. I need one function, a curve. That's actually what we do in standards. This curve has a parameter about the building. It's called T, the fundamental period of the structure. I'm going to tell you what is that in a little bit. And here is the acceleration of the structure, or the displacement of the structure. And your curve is going to be something like this. And basically, you're going to do solve one equation, or actually apply one simple parameters to find what is the value of Q in the structure. You get in this curve, you find what is the value of U. That is what the codes is doing. This concept is called response spectrum method. Right? This is very, very important method when it comes to seismic design. You have to know that there's a method that's called responsive spectrum. So let's see what responsive spectrum method is. Before you talk about the responsive spectrum method, I want to talk about something very quick. Let's see what is T that I put in this curve. As I said, we need to come up with a curve. This curve is something like this. Has T here, which is called the fundamental period of the structure, and has the acceleration A, which we call it here SA, the spectral acceleration. We're gonna know what the spectral acceleration is, and then you're gonna end up with like a curve, something like this. This is very, very famous curve in our structural engineering world. It's called responsive spectrum curve. All right, to know this, let's talk about the fundamental period of the structure. So, let's say this is my structure, okay? All right, what is the fundamental period? The fundamental period is the time that your structure is gonna take to make one cycle around it's a central line. Like, let's say my structure is like this. So what is the time that your structure under vibration is gonna go this and come back to the original place? That is called the fundamental period of your structure, to make one cycle around your structure. But the thing is, you should ask me a very, very fundamental question. What is it? But what if my structure is gonna move the other way? It's gonna have different period. Like, your structure is gonna move that way. So it's still the time that your structure is gonna take to go this, and come back to the original place. What if your structure is gonna have torsion? Same thing. The time that your structure is gonna take to make this and come back to the original place. So that means that your building has multiple periods. Depends on what? Depends on how the movement look like. So, and this is actually depending on the node shape of the structure. And by the way, look at this. I said in this way we have a period, right? And this way we have a period, and this way we have a period, right? But what if my structure is not moving that way? Like I said, my structure is gonna move this and this. In tall buildings, some structure make like this. This is another period that the structure can have. And sometimes the structure can move two nodes, like something like this. You're gonna tell me, but I never saw a structure doing this before. Right? I can imagine that your structure, even you never saw the structure is making this. This displacements happen, but it's very, very small that you can't recognize it. But the thing is, the contribution or the main displacement is the one that make like this. This one, like make like this, is very like minimal, but it happens. That's what we call the node shapes of the structures. The thing is, if your structure is a single degree of freedom like this, it only has one node shape. What is this node shape? It is this. It's either move like this or move like that. But let's talk about the mood shapes of multi-degree freedom system. Like let's say your structure is something like this, multi-degree freedom. The thing is, the degrees of freedom depends on the number of nodes. You have 1, 2, 3, 4, 5. So you have 5 mood shapes. And I'm gonna draw them for you right now. That's 1, 2, 3, 4, 5. Your structure can move that way. That has period. T1 can move like something like this. T2 can move something like this. T3, T4, T5. You'll tell me, oh, I never saw structures doing this before. No, it can do this, but you will barely see it. And this depends on something called the mass participation factor. Most of the mass make that movement, and maybe I would say 90% of the movement is that movement. And maybe you have 5% that movement, 3% that movement, 1% that movement, and let's say 0.05% that movement, and maybe other movement, whatever. Let's to complete the 100%, I'm gonna put 1. So with 1% of the movement that way, you barely can see it because most of the movement is coming from this one. That is the bird. And by the way, this is only in one direction. In the other direction, you are gonna have other mood shape. Torsion has mood shapes also, but we usually try to make our buildings doesn't have the diverse mood shape torsion. Because torsion is really, really bad. We are trying as structural engineers to avoid the torsion as much as we can. So if you have a structure that exposed or showed torsional mood shape as a verse mood shape, which is what we call it the fundamental period. The verse mood shape T1 is called the fundamental period, which is the highest period. Usually the structure tries to find the weakness in your system. Like if your system got a specific load, the weakest movement is gonna happen. Like let's say your structure is weak that way, so it's gonna move in the weakest system. Like, or let's say that structure is gonna have like let's say, I'm gonna give you a really, really good example. Like let's say you have, this is the plan of your structure, and this is the center of mass of your structure. I was like, oh, my structure is really, really weak, and I'm gonna put a shear wall here. All right? There's something called center of mass, and center of rigidity. Center of mass, this is your slab, and this is the source of the mass. This is the center of your mass. The rigidity is the columns and the walls that make your structure rigid. So the thing is, before you have this wall, the center of mass was like in the same was the center of rigidity. If you have the distribution of the columns are symmetric, like something like this, and you have a column here, column here, column here, column here. Center of mass is at the center of rigidity. But once you convert this column to a big shear wall, you make the center of rigidity to move towards the shear wall. Like it's gonna move that way, for example. Because the thing is, this shear wall is to the left and up, so the center of rigidity is gonna move up. There's methods that you can find the center of rigidity. By the way, have you guys did the center of mass calculation in dynamics or other classes? This is how you calculate it the same way to get the center of rigidity. And then if an earthquake happened, usually the force of the earthquake hit at the center of mass and make a moment around the center of rigidity, around this center. So basically, I want you to imagine with me, this is my slab system, and you have a very, very stiff element here, and there's a load that's hitting this slab. What is gonna happen to this slab? It's gonna make like this. It's gonna be shaking like this. So that is a torsional mode. You don't want this to happen in your system. So if you wanna make this system much better, I would put a shear wall here to bring the center of mass with the center of rigidity, or not to make them on top of each other, but at least make them close to each other. Okay? So this is gonna be much better system. Right now, rather than this one is gonna move that way, no, I have another system. So it's rather than making like this, we can make like this. Because the thing is, twist torsion is make a lot of shear on the columns and the shear wall. You don't want that, okay? So that is for this one. And as I told you, usually when an earthquake happen or when a vibration happen in your structure, it's always looking for the weakest movement. You have a very strong element here, so this is the weakest movement. You cannot force your structure to move that way. It depends on how you organize the geometry of the shear walls and everything. So the torsion is gonna happen anyway, you like it or not like it. So that depends on how you distributed the most stiffness element in your system. But let's say that we made our system really good and this is our first degree of freedom. This first degree of freedom is gonna generate the fundamental period of the structure, and it has the most movement of the structure, and most of the masses, 90% are moving that way. We try as a structural engineer to make the first moon shape is an X or a Y movement, and 90% of the mass are doing this movement. Okay? All right. So if you want to find the equation for T, usually we start with frequency. Frequency is equal to, we can call frequency or the radial velocity. Like let's say that you have a circle, okay? And this is the point. So the time that your point is gonna go and come back to the original place, so it's gonna be 2 pi. 2 pi is the distance, the radial distance that you did. Over time t is gonna give you the radial velocity. So omega is equal to 2 pi over t, which is the period. Same thing happened here. By the way, if you try to track the displacement that happened here, it's gonna give you a circle. You are gonna go that way, and you are gonna come back to the original place. So you cut 2 pi over t, and that's just gonna be equal to the frequency over the radial velocity. So then you can say that t is equal to 2 pi over omega. The period of the structure is gonna be equal to 2 pi over omega, the radial velocity of the structure. And the thing is, it was proven that the omega is equal to root k over m. The frequency of the structure is the square root of the stiffness over the mass. So if you want to substitute this here, so t is going to be equal to 2 pi multiplied by root m over k. And that actually makes sense. Let's assume that this is my structure. The more the structure is stiff, like if k is really, really big, what is going to happen to your structure? The movement is going to take less time to do the one period. Like if this is really stiff, it's gonna move but if your structure is flexible and the k is small, so it's gonna take much time, it's gonna make like this. If the mass is small, like this mass is almost like very, very small, so your structure is not gonna go that far, it's gonna go like something like this. But if there's this mass is really big and you have a mass here, this thing is gonna be very, very making a lot of difference. So the time is going to be much bigger. This is also very, very important equation in dynamics. All right, so we had this equation and we had this equation. This gives you the fundamental period of the structure. So I'm going to ask you, the acceleration of the structure, what does the acceleration of the structure depends on, and what is the fundamental period of the structure depends on? Can somebody tell me?
The mass and the stiffness.
Mass is stiffness and damping. That is the acceleration of the structure. How about the period, t? Does it depend on the mass? Does it depend on the force that the structure is going to be applied? No. It is depends on the characteristic of the building. Depends on its mass and stiffness. And by the way, same equation does exist if you included the damping. This is called undamped period. So if you have damping period, you are going to see the damping coefficient somewhere in the equation. But I don't want to overwhelm you with a lot of equations. Let's focus on this one. So I'm going to continue the concept of responsive spectrum next time, but I want to finish this lecture with one thing. You have to understand the fundamental period of the structure is like the fingerprint of your structure. Something attached to the structure. Doesn't depend on the load applied on the structure. Doesn't depend on the earthquake. Depend on the structure itself and its parameter. Okay? Doesn't depend on whatever this earthquake is big, is it small. Every structure has its own fundamental period. It depends on its mass, stiffness, and the potential of this structure to dam the force of the earthquake. And let's say you have a tall building and a small building. This small building is going to have period, and this tall building is going to have a different period. Even if you have two similar structures in the same construction zone, same buildings, but the thing is, you are not sure that the environment of construction of this building was the same like here. Like let's say you did a concrete element in this structure, a concrete element in this structure, but one of them the concrete wasn't that good. Or the concrete was, sometimes when you pour concrete, you have some holes, some like nesting happen. So elements are not gonna be the same. Soil is not gonna be the same. Everything might not be the same. So every structure has completely different period. However, sometimes we simplify. Oh, this structure is the same like this structure, so they are gonna have the same period. But in real life, none of the structures are gonna have the same period because they have different soil underneath them, different structural element, different loading at the same time of the earthquake, because this mass include the what we call the sustained mass in the structure, like which is definitely the dead load, because the dead load is not gonna go anywhere, and the live load during the earthquake. All right, which we assume that because the thing is, when we design gravity load, we assume all the live load is there. But when the earthquake happened, we go less extreme, that not all the life load is there. But anyway, I want you to understand this and the other equation over there, because these are the two most important equations to start. I don't want to say next lecture, but maybe the lecture Tuesday next week, because next lecture I'm gonna show you the project, so that you guys can start building your own project. But these concepts is really, really important. Okay, see you guys.
Thank you.
Thanks.